All right, so to analyze precision uncertainty, we're going to have to look at and actually basically work with the Gaussian or normal distribution. Now, there's lots of different distributions. There's the beta distribution. There's the Poisson distribution. You can use those for different types of essentially error or to kind of analyze systems. But the Gaussian is probably the one you're going to use 99% of the time, especially when you're looking at and working with error and when you're looking with a lot of phenomenon as well. So let's go ahead and let's look at our Gaussian function, or sometimes called the bell curve, although I doubt many of you have actually taken a course that's actually curved. But your Gaussian is centered around 0. It is a continuous curve, and if you're actually looking for the probability of finding a measurement, we can't just plug in, and we're not given, the probability is not just plugging into that Gaussian function. The probability will be integrating the probability of finding a measurement between two bounds. And this makes sense because, like we said, there's no probability of just making, you're never going to give me a single value of a measurement. You're going to give me a probability that falls between these two bounds. And this is related to our confidence interval. Now, if we integrate this curve from minus infinity to infinity, it's basically saying what's the probability that I measure, for example, a length that's in between minus infinity to infinity. That probability should be 100%. And we see with the Gaussian function, it is indeed. And our Gaussian function is defined as this, where mu is our population mean, and that's an important distinction. Our population mean is different from basically like a sample mean. Population means are really never known. Same thing with population standard deviation sigma. So that's the mean of population, pop, standard deviation. So, excellent. When you have outliers in data, there's actually a quantitative measurement in between there. So if your data point exceeds basically 3 sigma, so if my measure and is greater than basically my mu plus or minus 3 sigma, where it's greater than or less than respectively, right? Greater than plus 3, less than minus 3, then that is indeed an outlier. Now, we just kind of mentioned, we threw it out there, we never really know the population mean or the standard deviation. One of the ways that we can basically simplify this function so we don't have to plug that in each time is by basically defining a dimensionless variable, an arbitrary variable z, plugging that into this equation here. We can set this as 1 if we're just looking at the standard Gaussian. And this is going to be the Gaussian, the PDF that we're going to use and actually analyze in order to find those probabilities or to find those confidence intervals. So confidence interval is just basically saying in between x1 and x2, I am confident that 95% of the data falls between those values, meaning between x1 and x2, we should expect a probability of 0.95. So this value and this value would be your 95% confidence interval because between them, that's where 95% of the data falls. That's it. So I think a lot of people have trouble with this kind of concept of confidence intervals, but that's really all it comes down to. So you can actually calculate and solve for some of those, but I think I like to do it with an example. Now, there's a lot of different ways that you can find essentially confidence intervals and some of these values, and a lot of them use tables. And we may reference this moving forward, but you know what? In this class, we're going to actually calculate this and just integrate. We have programming tools. We're engineers. I think we can move past the tables. So let's go ahead and let's actually calculate and solve some of these problems. So I'm going to go ahead and define right here. I've got this z table, or working with z tables, but we're not going to actually do that. So it's saying, I got my PDF and I've got my z function solved for it here. So right now, it's saying what's the area under my standard curve between z of minus 1.43 and 1.43. So this would be my area. So I would have 84.7% of the data falling between minus 1.4 and 1.43. Then it's asking what range of z will contain 90% of the data. Well, I can basically integrate this and solve for those values of x that give me 0.9, and I see that. And now I can just plug this in here, and I can say, it'll be just between plus or minus this value for z. Let's do another example. Let's look at this E. coli example. So measured E. coli 135 times, Able particle tracker. We found a population mean. We find a standard deviation of 0.1. interested in these measurements, 2.875, 3.3, I plan to claim that 95% will fall within this range. Well, if we look at those values, 2.875, our measure z, remember, is x our measure mu is our population mean, population standard deviation. It's falling between minus 1.43 and 1.43. So we know already, and we can integrate it if we want, that's not going to give us 95% of our data. That's actually going to give us this same value here. So actually, I'm just going to steal this. But actually, I'm going to integrate from, remember, small value to large value. Let's put that in right here for positive x. 84% of the data. So that's not going to work. So how can we actually find those values? Well, I'm going to go for 95%. My z will be plus 1.96, and plugging in here and solving for x. So my true measurands that give me 95% of my data will be 2.8 and 3.196. Makes sense because we had smaller percent of the data to get 95. We need to widen those bounds effectively. Fantastic. Now, let's do some other examples quickly here to get our hands ready to go. Population of marbles, measure the diameters, population mean is 200, standard deviation is 20. I want to find 60%. We can do the same way. So I'm solving essentially for those bounds. I'm going to plug it into my z function, and those will be my bounds. Great. UTS, working in materials company, blah, blah, blah. What's the probability to find a sample that exceeds 350? So if I'm looking at exceeding 350, I want to integrate this from that z value of this 350 to infinity, right? Because I want the probability to get everything beyond 350. So that's just going to be my integral range. Nice. Voltage, 150 experiments, population mean. How many will be between 10 and 15? So if I have those two bounds, I can just go from here to here. I'm asking how many measurements, so I'm going to multiply by the total number of measurements, which is 150. And there we go. And then finally, let's look at some of these pressure. How many experiments will fall between 35 and 45? So again, plug those in. Two z values here, lower, higher. Less than 35, so I'm going to have to go from minus infinity to 35 here. And then finally, less than 45. Similar thing, we just change that here. And that's it. Isn't it nice not to have to use the tables? So we'll see in the next video and in the next lecture where we're going to get into, let's go over here. We're going to look at t-test, central limit theorem quickly, p-values, and hypothesis testing. So we'll see you then. Thanks. Bye.